Hey everyone. Today I'm excited to talk about one of my favorite puzzles, the 15 puzzle. I've got a basic strategy for solving this puzzle, but I wanted to find the optimal solution to solve any puzzle with the fewest moves. In this video, I'm going to show my problem solving process. First, how to build this game in Python and Pygame, then how to find the optimal solution using the IDA star algorithm. There's a link to the code in the description and some useful references if you want to learn more. So sit back, relax, and feel free to jump around to segments in this video that might interest you. We'll start by modeling the core logic of the 15 puzzles so that we can test our logic in the console. We'll build a puzzle class with a constructor that accepts the board size. That way we can play a 3x3 or a 5x5 puzzle, but we'll default to the 4x4. We're going to need a shuffle method, a move method, and a method to check to see if we won the game. I'm also going to create some global variables representing the directions that the tiles can move. On initialization, we're going to try to build a 2D array to represent the tiles on the board. We're also going to keep track of the blank square, since every move involves the blank square, and this will speed things up. We initialize the puzzle in the solve state, then shuffle. I'm also going to create a string representation of this class, so I can print it to the console. And I'm going to override the getItem method so that we can reference tiles with square bracket notation. The shuffle function will make 1000 random moves. We could randomly choose 2 tiles and swap them, but then we'd have to worry about parity, which basically makes sure that the puzzle is actually solvable. I'll put more information on this in the description if you're interested. Our move function simply checks if the input move is valid. If so, it swaps the blank tile with the tile being moved. We also make sure to update the new blank position. Finally, the check-win method iterates over the board to make sure each index contains the expected tile. Let's write some scrappy tests on the console just to see if our puzzle works. Create a couple test objects. We're going to shuffle them. We'll move every direction. We'll make sure we can't go out of bounds. And we'll even create a 3x3 puzzle. The other thing I'm going to do is when we initialize our puzzle, I'm going to comment out the shuffle so that we can see what a solved puzzle looks like to make sure our check-win function actually works. So the initial state looks good, and we can see that it's solved. Our shuffle function looks good. This puzzle looks sufficiently shuffled, and it is not solved. When we move left, we can see that the 3 has shifted over to the left. When we move right, we see the opposite. Moving up, I guess this was a bad case for testing move up, but we can at least test move down. Moving down 4 times. We didn't go out of bounds, which is good. And our last test is a 3x3 puzzle, which looks good. Before we forget, let's make sure to shuffle the board when we initialize a new puzzle. Now that we have a working puzzle model, we can build our game component using Pygame. The game module will start by initializing the screen elements, a puzzle object, and then define a very simple game loop. Handle input, then draw the puzzle. The entry point for this module will be the game loop. Keep in mind that this game loop is going to run at max CPU, so we can use Pygame's clock to limit the FPS. For input, we'll make sure to exit when the user closes the window, we'll shuffle the board when the user hits R for reset, and we'll make moves when the user clicks a tile. The only tricky thing here is mapping the mouse click position to an index in the puzzle. Drawing the board is going to require some constants for colors and fonts, which I'll initialize up here. To draw the puzzle, we'll loop over the puzzle, drawing rectangles for each tile, and center the tile number as text. The 0 tile is our empty space, which we have logic to draw specially. So let's try it out. We have our board here. It's been shuffled. And when I click a tile, it moves to the appropriate direction. And then I can click R to continue to shuffle as many times as I want. Sweet. So we've got a game that we can play. Now for the fun part. How do we write an algorithm that can solve this game in the fewest moves possible? I was thinking we could start with the strategy that I would use, which is solve the first row, then solve the second row, and then you could sort of solve the last 2 rows by doing some rotations of the last few pieces. I'm pretty sure that's not the optimal solution. I know a computer can do better. So one idea we could do is a breadth first search where we try every single move, starting from a scrambled puzzle, up, down, left, right. If that's not solved, go 1 layer deeper until you end up with a solved puzzle. The problem is when you do that, you're going to end up trying to traverse every single possible configuration of this puzzle until you find a solution. Since there's 16 tiles, we're on the order of 16 factorial different permutations of this puzzle. It's not feasible. We'll never finish that algorithm. So let's begin our journey reviewing the iterative deepening algorithm. Iterative deepening is a depth-first search with a depth limit on each pass. So when the depth is 0, we don't go any deeper than the starting node of our shuffled puzzle. Since we haven't solved the puzzle, we increment the depth to 1, which means we're going to do a depth-first search limiting to only 1 child node. We try to move right, that's not solved. We try to move up, that's not solved. We try to move left, and we try to move down. None of those are solved, so we have to increment the depth again. Now we'll do a depth first search limiting to 2 layers deep. So we move right, and we try to move right again. Not solved, not solved, not solved. That path is dead. So now we try this direction, and so on and so forth. So why iterative deepening? If you notice, it actually visits nodes in the same exact order that breadth first search would visit nodes. First, we check 1 move away from the starting point. If that doesn't find a solution, we check 2 moves away from the starting point. The advantage is we've saved ourselves a lot of space. Breadth first search would have to store the next moves at every single level, which would explode over time. Whereas iterative deepening only needs your depth, D. That's how many nodes it has to remember at any given time. It still has the same time complexity, though, as breadth first search, because ultimately it's doing a breadth first search, which in our case, the branching factor, how many children each node could have, is roughly 3. That's not the case for edges and corners, but if we take the worst case of 3, and we know that a 15 puzzle, at the worst case, takes 80 moves to solve, that time complexity is too bad to ever finish an iteration of iterative deepening. But we're on the right track because we've solved our space problem. Now, there's an algorithm called iterative deepening A star, which if you know A star, it uses a heuristic on breadth first search to pick a more preferable path at each layer. So instead of just looping through each possible child node, it's going to look at its children, and based on some estimate of how close that child is to the solution, it'll prefer that path. And if we can get a good enough estimate, we can pick the path without having to waste time exploring other nodes. Let's take a look at how the IDA star algorithm works in more detail. We have to introduce some new variables with IDA star. Every node is going to have an H score. That represents the best guess for the number of moves remaining until we find a solution. We'll have to write a function to return this value. More on that later. G is going to represent the number of moves taken to get to the current state from the starting scramble position. We start with G equals 0, and then every time we make a move, we increment G by 1. F is going to be the total number of moves, G taken so far, plus H, the number of moves expected until we find a solution for a given path. We also keep track of a global bound. This is going to be the upper limit for how many moves we expect the total path to take. At any point as we're exploring branches, if our F score exceeds the bound, we're going to stop looking at that branch. Lastly, we keep track of a min. This is going to be the best path that we've found so far among our child nodes. So to start off, let's say that we get an H score of 38 for this initial scramble. I'm just telling you it's 38, but we'll explain why we got 38 for this particular puzzle scramble. We start with our bound also equal to 38 because that's our best guess so far, as we assume our heuristic says that's how many moves it's going to take to find a solution, and so that's the boundary that we're going to hold ourselves to. Our minimum so far, we haven't looked at any child nodes, so we'll say that's infinity. So the first thing we're going to do is start exploring child nodes, and we're going to calculate those same variables. Our H score we get is 39. Now, what this tells us is that our heuristic function thinks that this puzzle state is farther away from the answer than the parent puzzle state. And when we add the expected moves remaining plus the moves we've taken so far, we get an F score of 40, which basically means we think that if you continue down this path, you're going to find a solution in 40 total moves. That's greater than our bound. Our bound is the upper limit for the number of expected moves. So we're going to stop exploring this path. But before we do, we're going to keep track of the minimum because that is actually the most promising path we've found so far. We try the next move. We find the same thing. Our heuristic function says that this state actually looks worse than the parent state. We have a F score of 40 that exceeds the bound, so we're not going to continue down this path. We try the next move. Now our heuristic function shows 37, so it seems that we're on the right track. With a G score of 1, it's taken one move to get here so far. That gives us an F score of an estimated total path of 38 moves to find a solution. Since our F score is within the bound, we are going to explore child nodes of this path. So we pick our first direction by moving the 15 square up, and what we find is our heuristic function says this is worse. So instead of being 37 moves away, we're actually 38 moves away according to our estimate. We've moved 2 moves so far, so that gives us an F score, meaning our total estimated path would be 40 if we continue down this route. That exceeds the bound. We stop exploring this node. However, we want to make sure to track so far, given this path, we can get there what we think in 40 moves. We try the next child, and we find the same thing. Our heuristic function shows 38. We add 2 moves that we've taken so far, and so the rest of this path appears that it'll take 40 moves. So this whole chain is now dead. We no longer want to continue exploring this path because we couldn't do better than or equal to the bound. So we try our last path from the parent, and we find that it's a better heuristic, so we're moving in the right direction. Since we're underneath the bound, we're going to explore these children. And what we find is that child, if we were to slide this 2 over to the right, it does not appear better. The heuristic shows 38. We've moved 2 moves so far, and so the estimated path would be 40 moves total. So we're going to keep track of this, that if you go this direction, we can at least do it in most likely 40 moves. And we'll try the next child, which we see is a heuristic of 38, plus we've moved 2. And so again, we find that this total path would likely be 40. And so we stop because that does not beat the bound. And finally, this path is exhausted. I think there's more children, but hopefully you get the idea. So we come back to the parent. We've evaluated all children, and we couldn't beat the bound. So what we do is we take the minimum path, expected path that we found so far, and we reset the bound. So now the bound is 40. And we iterate. That's the gist of IDA star. So here's kind of a summary of all the paths that we've taken. And on our next iteration, we'll do the same thing, but there's a new bound of 40. So you can imagine as we go into this first path, that F score is 40, which actually is on track for that bound. So we would explore those children. Similarly, if we make it to one of these nodes, one of these children, those F scores are also 40. So we could continue down those paths as well. Now that we understand the IDA star algorithm, it's time to talk about the heuristic function, because this is where the magic happens. Imagine picking a constant heuristic. Say it returns 10, no matter what puzzle state we give it. So for this initial scramble, we think we're 10 moves away from the solution. Well, when we look at the child nodes, those also look like they're 10 moves away from the solution. And when we look at those child nodes, they also look like they're 10 moves away from the solution. So no path gets any sort of preferential treatment because it looks to be closer than the other. Well, we end up reverting to iterative deepening. Now, imagine picking a perfect heuristic, a heuristic that always returns the exact number of moves needed to get to the solution from the current puzzle state. So for this first state, it says 38, and if that's the exact number of moves remaining, as we look at the children, any child that is not the correct direction, our heuristic would not show 37, it would show 39. And the correct solution would show 37. And underneath that child, the correct solution would show 36. So you could find the solution very quickly if you had a perfect heuristic function, because all you have to do is look for the child where the heuristic decreases. Unfortunately, there is no perfect heuristic function for this puzzle, at least within reason. That's why this becomes a challenging problem, because we have to define a heuristic function which takes some kind of estimate. The last scenario I want to think about is if we were to overestimate our heuristic. What I mean by that is if our heuristic says that we're 38 moves away, but we're actually only 20 moves away from a solution, what happens? Pretend the solution lives in this far left branch. However, we've overestimated our heuristic. We're only 20 moves away, but it looks like we're 39 moves away if we were to go this path. What could happen is that we might find a more favorable path according to our heuristic function that says we're only 37 moves away. We might find 36, 35. We might find a solution over here in 30 moves. So we never actually gave the far left path a chance because it didn't look favorable, just because we overestimated the heuristic. So that's why we always want to underestimate the heuristic. Another term for this is saying that the heuristic is admissible when the heuristic value is less than or equal to the exact solution. Now, sometimes you may want to allow overestimating the heuristic and choosing that less favorable path, because you could actually find a solution quicker. The problem is it will not be optimal. It could be suboptimal. In this case, we want to try to find the best solution, so we're going to only look at admissible heuristic functions. The first heuristic function we're going to look at is called the Manhattan or taxicab distance. For each tile, we count how many moves away it is from its position in the solution. This is admissible because it's impossible to move a tile to its destination space in less moves. So, for 7, we would have to slide it to the right 2 and down 1, assuming it was unobstructed, for a total of 3 moves. For 10, we would slide it down 2 spaces to get to its destination space. And we repeat that for every tile in the puzzle. This gives us a total heuristic of 38 using the Manhattan distance. The solution is fast to calculate, but it's not very accurate, since it's likely that pieces will be in conflict with each other on their way to the destination, requiring more moves than calculated. One way we can improve on this is to count linear conflicts. To find a linear conflict, we look for 2 tiles that are in their destination row or column already, and they're out of order. So 2 needs to somehow get above the 10, and 10 needs to somehow get below the 2. Using Manhattan distance, it looks like 2 is only 1 space away from its destination, and 10 is only 2 spaces away. However, we know 2 would have to slide over so that 10 can go down, and then 2 can slide back. Or vice versa, some way these tiles need to get around each other. So that would take 2 extra moves. Another linear conflict on this puzzle is the 6 and the 4. These are both in the correct column already, but they're out of order. So somehow 4 needs to get around the 6. So what we can do is take our Manhattan distance and we add 2 spaces for every linear conflict that we can find for a heuristic of 42. So we're getting closer. This next idea is the holy grail of heuristic functions for the 15 puzzle. As a disclaimer, these are not my ideas. If you want to learn more, check out the research paper titled Additive Pattern Database Heuristics, linked in the description. This paper was co-authored by Richard Korf, the guy who came up with the IDA star algorithm. So yeah, this idea is no joke. Imagine we divide the 15 puzzle into mutually exclusive groups. Every tile belongs to a group, and no tile belongs to more than one group. If we take a scrambled puzzle, you can break out the tiles in each group. So if we look at this top puzzle, we see the 1, 2, 3, 5, and 6 belongs to this red group in our breakout to the left, and so on. Now, imagine we have a pre-computed database that tells us exactly how many moves it takes to get each of these groups in to the solved state. Now, one thing to note here is we don't count moves on unmarked squares. So what I mean by that is if we were to solve the 1, 2, 3, 5, 6 group, we're going to have to move some of these unmarked tiles to get the 1, 2, 3 into position up top, but we only count moves in this total when one of those grouped tiles moves. The advantage is we can take those totals from each group and simply add them together and safely be under the perfect amount of moves to solve the total puzzle. This is an admissible heuristic because no group can be solved in fewer moves than our pre-computed database, and we don't count moves on unmarked tiles because those moves would have been counted in some other group. It's not a perfect heuristic because some of these groups may have conflict with another group as it's trying to solve itself in the perfect number of moves. So, how do we generate the pattern database that tells us exactly how many moves it takes to solve each of these subgroups? For each group, we're going to use breadth first search to visit every configuration of the marked tiles in the blank square. Since all unmarked squares look alike, we can rule out many paths that BFS wants to explore. In fact, we end up with only 5.7 million puzzle states instead of 16 factorial if we were to include every permutation of the puzzle. To make sure that our heuristic remains admissible, we only increment the count when a marked tile is moved. When an unmarked tile is moved, that count would be included in another group. Once BFS completes, we can dump the minimum number of moves required to reach each permutation of the 5 tiles in the group, which is only about 500,000 puzzle states. At this point, we don't care about the blank square. Remember, we don't increment our count when an unmarked tile is moved, so no matter where the blank square is, the count would remain the same for that permutation of tiles within this group. A quick word on picking groups. We could use a 5-5-5 grouping, which we saw takes about 5.7 million iterations of breadth first search. A better pattern database is the 6-6-3 grouping, but that takes even more iterations, about 57 million. And better yet is the 7-8 grouping, which takes a whopping 4 billion iterations of breadth first search to calculate that group of 8. To save computing time, I'm going to stick with the 6-6-3 grouping for this video, but I challenge you to try to build a program to get the 7-8 grouping. Let's start by writing the code to generate our pattern database. This is essentially going to be a breadth first search on one tile group at a time. I added a parameter in the puzzle constructor to let us generate a puzzle in its solved state for the starting node. We use a hash set to represent the permutations of the puzzle group that we visited for quick lookup. We use a dictionary to store the minimum moves taken to reach each permutation of tiles for this group. And we use a queue to hold the next puzzle states that we want to visit. Before we continue, we need to write a hash function in our puzzle class to help identify unique permutations of a subset of tiles within the puzzle. My hash function will build a string of the x and y coordinates of each tile only within the group in order of the tile value. If a tile isn't inside of that group, it won't be included in my hash function. Now we can push our starting node onto the queue and start our breadth first search loop. We unpack the first node on the queue, then check to see if we've already visited this permutation, including the blank tile. We also check if we found a new permutation of the grouped tiles, excluding the blank tile, or if we reached an existing permutation in fewer moves than before. Now we can start exploring child nodes. I created a simulate move function that just returns a copy of the puzzle with the requested move being made. We check each direction, see if it's a valid node, and increment the count if a tile in our group was displaced. Once there are no unvisited permutations to search, we return our closed list. Our main entry point to this code will define the tile groups and call the build pattern database function for each group, then write the results to a file to be loaded in by our game. Let's add a few final touches. This could take a long time to run, so I'm going to add some logging in to help us monitor the progress from the console. Also, groups can be processed independently, so I thought it would be cool to process them in parallel. Now we're ready to build our pattern database. It's taking around 10 to 15 seconds to process 100,000 records, So this will probably be running for about an hour, 2 hours. In the meantime, let's start implementing IDA star. The driver function will start by setting our bound to the H-score of the scrambled puzzle. We'll define our H-score function later. We'll need to keep track of the path and directions we've taken so far. Until a solved state is reached, our algorithm is going to execute a recursive search, which will either return true if a path is found within the number of moves defined by our bound, infinity if no path is possible, or the minimum feasible path that our search discovered, which we'll set as the bound on the next iteration. The search function first calculates the heuristic of the puzzle state that we're evaluating and determines if we've exceeded the bound or if we're at a solved state. If we're not solved and still within the bound, we'll execute a recursive search on all possible directions from the current state, except for the previous direction to save some time. Every time we go down a level in recursion, the G parameter increases by 1. If the bound is ever exceeded, the recursion will unwind and we'll keep track of the minimum path we found so far. Once the solution is found, the directions array will contain the optimal moves needed to go from the initial scramble to solved. Now to load in our pattern database and write the heuristic function. We can load in the groups and pattern database using Python's pickle module, which we use to write the files in the first place. In the IDA star driver function, we can initialize the database in case it hasn't been loaded in yet. Our heuristic function will loop through each group and look up the subpuzzle hash in the appropriate pattern database dictionary. If an entry isn't found for some reason, we'll resort to using the Manhattan distance. This should never happen, but it's useful for debugging if there's any issues in our pattern database. Finally, we can wire in our new AI logic to the Pygame component. When the user types the H key for help, we'll store the results from IDA star and make one move. If the puzzle is ever solved, we reset the AI moves. We should probably also reset the AI moves if the board is shuffled. And that's it. Once our pattern database is finalized, we can test it out. All right, time to see what our AI can do. The game takes a few seconds to load now because it's preparing the pattern database. So once the puzzle is scrambled, I press the H key to trigger IDA star. There we go. Took 7.5 seconds to find an optimal solution of 49 moves. So I can keep pressing the H key and we'll watch it go through every single move. We can see what the optimal solution looks like for this puzzle. There it is. Pretty cool. So I can just do some manual scrambles, rotate some pieces, and we'll see what IDA star can do on a very poorly scrambled puzzle. It can find the solution in 14 moves, less than a second. Nice. And that's all I have for you today. If you made it this far, hopefully you'll learn something new. If you have any questions or suggestions, I'd love to hear about it in the comments. If you enjoyed this video, you want to learn more about algorithms and solving games with AI, subscribe to my channel to get the latest on my upcoming projects. Thanks for watching. Have a nice day.